In the previous module, we have seen techniques to find out the variations of a data series. The variation of each and every unit of data from its central value. And we have calculated different measures like range, total deviation, mean deviation, standard deviation, variance, etc. And of course, we have calculated the coefficient of variation and standard error also. So, in any such numerical data, when you calculate the central tendencies and then you calculate the measures of variation, or which are also known as measures of deviation or dispersion, the data will be providing you, or the results will be providing you certain extent of variations in all the cases. Since the central value is a calculated value and each and every value of x vary differently from that central value. And what may be the reason for this variation? That's the next question. Since you are collecting data from a numerical population, a living population, or another population which is having certain particular properties like that, each and every individual of the population or each and every unit of data collection will be showing some difference from the other. And that's the reason for this type of variation. And of course, variations may occur due to several reasons, and you see, you can attribute these variations to some experimental differences, some differences in the properties of these two groups, of different groups, and you can find out the differences between the groups based on the measures of deviation when compared along with the mean values. And what may be the reason for this variation? Maybe it is simply due to chance variations, or it may be due to certain properties of these populations which are different. When you are comparing two plant populations, for example, the first population may be a variety and the second population may be another variety, and the difference in fruit yield may be due to the varietal difference, or it may be simply due to chance. If the variation is high, evidently it means that there is difference in yield between variety A and variety B. And if it is low, if the variation is very low, or then the reason may be simply chance. So, if the variation is high, it may be due to some reasons, and of course, the results or the suggestions after the analysis should say about it, and in further studies should be requested to find out the reason for the variation. On the other hand, if both of them are same, or the variation is very not very significant, very large, it may be due to chance, and we may be able to say that variety A and variety B, even when they are two varieties, their behavior is almost the same. So, how can you say it systematically and scientifically based on evidence? Of course, if the coefficient of variation of a character in variety A is low and variety B is high, you can say that the first variation is showing lesser variability and the second population is showing higher variability. Here the question is whether the variation between the two groups is significant or not. And for the purpose, we go for different types of tests. They are called tests of significance. And the present module deals with tests of significance. Tests to see whether the variation in A and variation in B, the variation in population A and variation in population B, or variation of a particular variable, the variable X in the first population and the variable X in the second population, whether the variation is significant or not. So to find out that, we carry out certain tests, and they are called tests of significance. And there are several tests used for under different situations. T-test, Z-test, chi-square test, F-test, etc. Some of them. And they are used for different purposes and under different situations. And to test the significance of variation between the population A and population B, or the sample A and the sample B, you have to study the properties like central tendencies and variations first for the mean and standard deviation. For example, are to be calculated first. Or mean and variance are to be calculated first. And after that, you have to decide a particular test that can be used for that particular purpose, in that particular case. And in statistical interpretation, usually, at the time of testing significance of variation, we make certain hypotheses. You can make a hypothesis means that you can state that there is no significant difference between the variation in population A or the variation in population B, or there is no significant difference in the case of the behavior of the variable in population A and the behavior of the variable in population B. There is no significant difference. Or you can state it the other way also. There is significant difference in the case of the behavior of the particular variable, the variable X in the first population and in the second population, or in the first sample and the second sample. So there is a hypothesis which says that there is no significant difference, and there is a hypothesis saying that there is significant difference. And the first type of hypothesis which says that there is no significant difference between the treatments, the samples, in the case of a particular phenomenon, in the case of a particular character. Such a hypothesis is known as a null hypothesis, which says that there is no significant difference. And the other type of hypothesis is the alternate hypothesis. And in that, you will say that there is significant difference in the case of a particular phenomenon, a particular variable, in the case of the first population and the second there are null hypothesis and alternate hypothesis. Null hypothesis state that there is no significant difference between different situations or treatments being analyzed in the case of a particular variable. In other words, it states that the deviation from the expectation, if one is considered as the expectation and the other is considered as the observation, for example, there is no significant variation in the case of deviation of the variable in both the cases, and so you are stating that the variable behaves, or the variable shows no significant variation between populations, between samples, or between treatments, like that. So that is a null hypothesis. And then comes the other type of hypothesis, which is called the alternate hypothesis. And here we say that the hypothesis states that there is significant difference between the different samples in case of the variable. Or when you are comparing an observed set of data with an expectation, statistical expectation, probability expectation, for example, you will say that there is significant variation. So, between the two. So, you can formulate either a null hypothesis or an alternate hypothesis. But in statistics, the usual practice is to formulate a null hypothesis stating that there is no significant, or the variation is not significant, there is no significant difference. And if there is no significant difference as found out by your further analysis, but your test of significance, you will accept the null hypothesis, and if you find out that there is significant difference between the two groups, you will reject the hypothesis. So, that's about testing of hypothesis, and there are different types of tests used for that. And here, just before that, we have to find out, or we have to get details about certain terms and definitions used in tests of significance. So here we have already discussed about the significance of variation. It is the different, you can see that there are different measures of a variable observed from a population, and even when you are conducting, or even when you repeat the same experiment 2 times, the value of, for example, the value of standard deviation calculated from the first experiment, and the value of standard deviation calculated from the second experiment using the same protocol, using the same standards, same types of units of data corrections, same methods of corrections, same environmental conditions and all that, or if both the treatments are essentially the same, even then there will be some differences between the values obtained as central values and deviations of population A, I mean sample A and sample B, treatment A and treatment B, for example. But the thing what you want to know is to see whether this variation is statistically significant or not. And if it is, the variation is not significant, it may be due to chance. And if it is significant, it means that there are certain differences between two study populations, to the two treatments. And the tests usually used for the purpose, the tests of significance that are usually used for this purpose are t-test, chi-square test, etc. T-test, chi-square test, and of course F-test also. F-test is usually used when there are more than two situations to be compared. In simple tests like t-test and chi-square test, you can compare two situations, population A and population B, sample A and sample B, treatment A and treatment B. Observation and expectation. When there are two groups of data, you can use t-test, chi-square test, etc. And when there are more than two groups of data in the case of a particular variable, or if you are collecting data from 3, 4 or 5 samples, the test statistic used is F and F-test, and the analysis of variation using F-test is known as analysis of variance or ANOVA, which we will be dealing with later. So presently, even though there are different tests and the different tests are used for different purposes, we will be dealing with the t-test and the chi-square test. And before that, we have to know something about certain usages in tests of significance, like critical region, critical value, etc. You see, you are dealing with a population and you can draw a frequency curve from the data, from the arithmetic mean of the population, of the different values obtained, and the each and every value. So if you are plotting each and every value on one axis, and if you are plotting their corresponding frequencies on the next axis, on the y-axis, you will be getting a curve, a frequency curve. And if the population is very ideal, it will be a well-shaped curve, we will say. Means towards the extreme sides, extreme ends of the curve, the frequencies of individuals will be, the frequency of units will be very low, and towards both the extremes and towards the center, the frequency will be high, towards the center values. So you get a well-shaped curve, and the well will be getting distorted based upon the irregularity in frequencies. So, if you are imagining such a curve, the critical region means the tail end of the curve, the tail ends of the curves. And usually, that region, the tail ends of the curve represents the critical region. That region, in that region the frequency will be, that region deals with the extreme values, and the frequency of such values will be very low. So in tests of significance, you will be calculating the test statistic. For example, you will be calculating the t value or the chi-square value, and then you will be testing whether the calculated value is significant. For that particular purpose, the distribution of these values, for example, the distribution of t or the distribution of chi-square, under different probabilities, are usually given in statistical tables that are available. So there are t tables, chi-square tables, f tables, etc. And in those tables, you will be getting the different values of t or chi-square, for example, at different probabilities. And you will be deciding a level of probability above which you will consider the variation significant or not. So you will be getting a value in the table, in the T table or chi-square table at that particular point, and the value at that particular point is known as the critical value. So you can divide the values or your calculated values into, because you can see whether it is below the critical value or whether it is above the critical value. So that's the region representing that such values are known as the regions representing such values are known as the critical regions, and the corresponding values are known as corresponding values. I mean the critical values. And when you come to the critical values, you have to know certain things more to decide which is the critical value to be considered from a frequency table. I mean from a table of the distribution of the test statistic like a T, chi-square, etc. You have to fix a level of significance. A level of significance or a probability level up to which you can consider that there is no there is no significant variation, and then the other part will be considered as consisting of the significant variation area. So there is a critical value, and based on the critical value, you will be either accepting the hypothesis or rejecting the hypothesis. So that is level of significance, and in the case of level of significance, usually you can fix a probability level. It can be 5%, 1%, 0.1%, etc. based on the nature of the experiment. In very simple terms, 5% means the extreme 5% of the values come under the critical region. So, depending upon the scope of your experiment, you will be fixing an appropriate significance level, and in common experiments dealing with plants, etc., it is 5%, and if you want a higher level of accuracy, you will move to 1% like that. So that is the level of significance. And one more thing you have to know before starting such an analysis, and that is a degree of freedom of the experiment. Degree of freedom means, tables of test statistics like the T table or the F table or chi-square table, degrees of freedom also will be given. Usually on one side the probabilities will be marked, and on the other side the degrees of freedom will be marked. So you have to look for the value of that test statistic at a particular probability level, at a particular degree of freedom. For example, T at 5% level for 1 degree of freedom. T at 5% level for 3 degrees of freedom. Or T at 1% level for 10 degrees of freedom, like that. So in that way you will be getting the data arranged in the tables of test statistic. And degree of freedom means the number of types of observations that are free to vary in a particular experiment. You see, when there are only two types of events, for example, if you are considering a group of data, a table in which the numbers of boys and girls, or the numbers of male children and female children in the childbirths in a particular district in a particular month, the details are given. There are only two groups. The first group is the group of males and the second is the group of females. So only there are two groups. In that sense here the number n, n in the case of the different groups, or the number of, if they are considered as treatments, there are only two treatments. Treatment A, treatment B, you can say, or males, females, or like that. When there are head states, there are only two groups. And when there are two such groups, I mean case 2 and k minus 1 gives you the degrees of freedom of that particular experiment. If you are considering an experiment in genetics with a tall red, tall white, dwarf red and dwarf white progeny, there are 4 types of progeny, and since there are 4 types, here the degree of freedom is 4 minus 1, it is equal to 3. So you can say it is k minus 1. Like that. So you can simply say in simple experiments the degree of freedom is n minus 1 or k minus 1 depending upon the case. And in the case of an unclassified data, for example in the case of an unorganized data, n is equal to the number of units. So usually in simple experiments n minus 1 or k minus 1 is considered as the degree of freedom. Degree of freedom is the individual choices. For example, if you have in your hand, you think that there are 4 sweets covered with different types of wrappers. A red wrapper, a white wrapper, a black wrapper and a green wrapper. And if you are asked to take one sweet from them, you can take the sweet with the red wrapper and keep it aside. You can take the sweet with the white wrapper and you can keep it aside. You can take the the sweet with green wrapper and keep it aside. But after that, if you are going to reject the 4th sweet also, you will not get a seed. So it means there are 4 sweets, you have only 3 degrees of freedom to select. So that's about degrees of freedom. So that these ideas should be known to you: the critical region, critical value, the level of significance, and degree of freedom. The critical value is a value that is obtained from the corresponding table of data statistic, and in computer programs of computer packages of analysis, usually the package will give you the critical value if you are providing the degree of freedom and level of significance. knowing these things, we have to move to two important types of tests. Test of or t-test and chi-square test. So t-test is a rather simple test which is used for different purposes, and the most important uses of t-test are to compare the means of two samples, or to compare a calculated mean with a hypothesized mean, like that. You will be having two mean values, you have to compare them. Or you will have two experimental populations and you have conducted a survey in the first sample, or you have conducted a study in the first sample and second sample. You have taken the number of fruits produced by a particular number of plants in a state in farm A and farm B, for example. So you have taken data from the first group and the second group also, or as I earlier mentioned, in the first you have taken only one set of data, but somebody have already reported a mean value for that. For example, if it is a seed company and if they have produced seeds, they have given an expected mean number of fruits from that particular variety, and you have to test whether that claim is correct or not. Or in the second case, you have two plots, and in one plot you are growing variety A, and in the second plot variety B. You have to compare them. Or simply you have two plots, and in both the plots you are growing the same variety, but there is difference in performance, maybe due to other reasons, due to difference of levels in fertilizer treatment, or availability of water, fertility of soil, etc. like that. So you have to compare the yield of the first plot with that of the second plot. So you are taking data from the two farms like that. So to compare two situations, you are using in that way. You are using t-test, and t-test of course has other uses, and one of such important uses is to test the significance of correlation coefficients. For example, a t-test is carried out to test the significance of correlation in correlation analysis. So in this case, now we are going to see an example of t-test to compare an expected value of mean with the mean obtained through an experiment. There are two mean values. One is an expected value, a hypothesized value, and the second mean has been obtained through an experiment. And you can compare them. And you can give the problem like this. It is given in the slide. It is claimed by a seed company that the mean number of fruits produced by a particular variety of chili is 100 per plant. They claim that the mean number of fruit production by this variety of chili is 100. And you are asked to conduct an experiment and to test whether the claim is valid based on the data obtained. So you are given such a data table in which you have used 12 plants in the sample, and you have recorded the number of fruits, annual production of number of fruits you have recorded, and you are asked to find out whether the behavior of this fruit production is as per the claim made by the seed company. And for that you are going to conduct a t-test, and the formula for t test is. So you see, in all these cases, we are carrying out tests based on the variability levels. Variances are calculated, and based on the variances or deviations are calculated. Based on the deviations, you are calculating the t value. So in the case of when you have one hypothesized value of mean and you are asked to conduct one experiment and validate it, t-test is conducted and the formula is t is equal to x bar minus mu divided by standard deviation by root n. T is equal to x bar minus mu divided by sigma by root n, small sigma by root n, or you can also write T is equal to x bar minus mu divided by smallest by root n. Smallest stands for standard deviation. So what are the different steps? The formula is T is equal to x bar minus mu divided by smallest by root n. X bar is the calculated mean, the mean which you are going to get after your experiment. Mu is the given value, the claim of the company. They have claimed that 100 is the mean number of fruits that are produced by this variety of chili. And S is the standard deviation that is going to be calculated, and N is the size of your size of the sample. So you have taken 12 grams for the experiment. So the first step is you have to find out the fruit number in each case from all the 12 plants, and you are getting 12 values. And the next step is to calculate its mean. Since it is a simple, since it is a group of unorganized data, mean is equal to sigma x by n, and it is equal to 99. When you calculate it, you will get 99, and then you are calculating deviation. So mean is 99, and x has got several values. X bar is 99 and x has got several values. So you are calculating d, small d, x minus x bar in all the cases, and you get different values of x minus x bar. And the next step is to square them. You have to calculate the standard deviation. You see in the formula there is standard deviation needed. The things needed are the calculated mean, which you have already calculated, is 99. Then the mu is already given, it is 100. And then the next step is you have to calculate smallest, that is standard deviation of the experiment population or the experimental sample, and you have to calculate d square first, and you have to find out the total of d square, sigma d square, and its square root, and then divided by n. The formula of standard deviation is square root of sigma d squared by n, and you get square root of 352 by 12. 12 is the n, and the standard deviation calculated is 5.42. So now you have all the values. X bar is the calculated value of mean is 99, mu is 100, standard deviation is 5.42, and n is 12. So you are substituting in the formula, and you are getting 1.57 after your calculations as the t value. So calculated value of t is 1.57. Then you have to see certain things. You have to fix a level of significance, and since it is an experiment dealing with a plant population, 5% level is okay, and you have to find out the table value of t at 5% level for how many degrees of freedom. There are n number of individuals means n number of plants means 12 number of plants. 12 is the n in the case of the experiment, and n minus 1 is to be found out. So n minus 1 is 11. So t at n minus 1 is to be, or t at n minus 1 means t at 11 degrees of freedom. T at n minus 1 degrees of freedom means t at 11 degrees of freedom. So you have to go to the table of t distribution, and you have to find out the t value corresponding to 11 degrees of freedom at 5% value. And the table value, the value the subject from the table is 2.2. And it shows that the calculated value of t is 1.57, and it is lower than the table value. It is lower than the table value means the variation is not significant. So you are accepting the claim of the company. They claim that 100 is the mean fruit number of the variety of chicken. You are accepting that claim because the variation between the two, the first mean and the second mean is low. The hypothesized mean and the calculated mean is low, and under t-test you have seen that the variation is not significant. So you have decided, you have concluded that the claim of the company is valid. So that is the first experimental situation under which you are using the t-test. And you can see one more example in which you are using t-test under another experimental situation. Here, the t-test is used to compare the means of two samples, sample A and sample B, or plot A and plot B, when the variances of both the samples are known. You have conducted an experiment, or somebody have conducted an experiment, and you are given, or you have obtained data on mean yield and standard deviation, and of course the number of plants in the sample also. In the case of plot number 1 and plot number 2, either you have conducted the experiment and you have found out the mean and standard deviation from 20 plants in the first case and from 20 plants in the second case, based on the mean yield. And as per the data given here, in the case of the first plot, the mean yield is 120. 120 fruits are produced per year. And in the case of the second plot, it is 110. And standard deviation in the case of first plot is 10, and the standard deviation in the case of second plot is 20. And sample size in both the cases was 20. There is no rule that the sample size in the first case and second case should be equal, but here it is equal. So here you see you are using a different formula. The test statistic is t, and t is calculated using the formula. In this case, you use the formula x1 bar minus x2 bar divided by square root of s1 squared by n1 plus s2 squared by n. So what are these values? X1 bar, of course you know it is the mean of the first sample, the first plot. X2 bar is the mean of the second plot. So, and S1 is the standard deviation of the first plot, and S2 is the standard deviation of the second plot. N1 is the number of plants in the first plot, and N2 is the number of plants in the second plot. So now you know the values and you are substituting, hence T becomes, if you are substituting in the formula, it is 120 minus 110 divided by square root to all the items or the values below the line you have drawn below the 120 minus 110 to the complete denominator, and you see square root of S1 squared by N1, that's 10 squared divided by 20 plus S2 squared divided by 20. S2 squared divided by N2 means 20 squared divided by 20, and you will be getting the result as 2. So you have got a calculated value of 2 as the t value in this particular experiment. And here, so t is 2, calculated value of t is 2, and you have to see whether it is significant or not. And here also you are fixing the level of significance at 5% level. And here you see the degree of freedom is considered like this. Degree of freedom is equal to 1 by 2 into N1 plus N2 in brackets. Means you have to total N1 and N2 and divide by 2. 1 by 2 into N1 plus N2 minus 1. Something similar to N minus 1 also. Here, but it is, since there are two N values, it is 1 by 2 into N1 plus N2 minus 1. So here it is in the present experiment, it is 1 by 2 into 20 plus 20 minus 1, and you will get 90 as the degree of freedom. And the table value of T for 90 degree of freedom at 5% level is to be found out, and it is, the table value is 2.09. 2.09 is the table value, and the 2 is the calculated value. And here also you can see that the calculated value is lower than the table value. And what does it mean? It means that in this experiment also, the difference between yield in the case of the first plot and the second plot, even though the means are a little different and the standard deviations are also a little different, that difference is not statistically significant at 5% level. So here also you can say that both plots perform almost uniformly in statistical terms. So that was about t-test, and then comes chi-square test. And chi-square test is a type of test that can be used under a variety of conditions, under different situations. And one among such users, perhaps the most important among such users, is using chi-square for goodness of fit, for testing goodness of fit. Testing goodness of fit means testing whether an observed data fit to a theoretical expectation. Whether a statistical ratio can be fitted to the given observation. And that is goodness of fit. And that is one of the most important uses of chi-square test. And here we are now seeing an example of using chi-square test for testing goodness of fit. The example is chi-square test to test whether a set of observed data a set of observed data behaves as per a statistical ratio expected. Just to see whether a set of observed data behaves as per a statistical ratio expected. And the example is like this. It is given to you. A ratio of 1:1 is expected between male and female childbirths. Generally, that is your usual expectation. When you speak about childbirths, you expect a 1:1 ratio between males and females. In a data, if there are 100 children, you expect 50 males and 50 females. That's your expectation, and that expectation is based on the probability theory also. So you are given an experimental result here. In an experimental set of data obtained for a particular area, the following proportion was obtained. Test whether this distribution is as per the 1:1 expectation. So the expectation is 1:1, the expected ratio is 1:1, and the observation given is like this. In the case of 1,000 childbirths, maybe in a hospital, in a district for a short period like that. The gender is given, male, female, and observed values are like this. Male 530, female 470. There is some difference. And the total is 1,000. And so you are plotting it on a table, and the first column stands for the gender, male, female, and second column for the observation, O, 530 for the 70, 530 in the case of males and 470 in the case of females, and then you are writing down the expected value. The expectation is 1:1. Totally there are 1,000 individuals, and there are two types of data, two groups, the number of males and the number of females, and your expectation is 1:1 means you expect 1/2 of the total number of childbirths as males and 1/2 of the total number of births as females. So the expected values are 1,000 into 1/500 in the first case and 500 in the second case. So you have written down the value of E in both the cases. And the next, you see here the formula for chi-square is a measure of is a test statistic, and it is calculated based upon the ratio between the difference between observed values and expected values and the expected values. You are analyzing the difference between the observed values and expected values based on the expected values. So the formula of chi-square is sigma O minus E, the all squared by E, it is given in your table. Chi-square is equal to sigma O minus E all squared by E, and O minus E is the difference between the observed value and the expected value. And in the first case, in the case of male, the difference is 530 minus 500, it is 30. And in the second case, it is 470 minus 500 is minus 30. And since you are taking O minus E the all squared, when you square both these values, both of them will be becoming positive. So O minus E all square is to be found out, and the first case is the square of 30, it is 900, and the second case also it is 900. And next step is to find out O minus E the all squared by E, and when you are dividing O minus E the all squared with the corresponding expected values, O minus E the all squared by E divided by 500 in these cases. In both the rows you will get 1.8. The chi-square value is 1.8 in the first case, and in the second case also it's 1.8. And to find out the total chi-square, you have to sum them together, and you have to take the sum of 1.8 plus 1.8, and it is 3.6. So you have calculated 3.6 as the chi-square in the given experiment. And here also you have to see whether this value is 3.6 is statistically significant or not. And for the purpose you are using a chi-square table, which is almost similar to a t-table. It is available with n on one side and the probabilities on the other side. And here also you are fixing 5% as the level of significance. And if you are going to the probability, to the table of chi-square distribution, here the degree of freedom is k minus 1. And here k minus 1, there are two classes, male and female, and k minus 1 is equal to 2 minus 1. 2 minus 1 is equal to 1, and chi-square at 5% level for 1 degree of freedom given in the table is 3.84. So you get 3.84 as the critical value of chi-square at 5% level for 1 degree of freedom, and your calculated value is 3.6. Means that the calculated value is not significant. You see, apparently there is some variation, 530, 470, you may think that it is significant variation, but when you have carried out a chi-square analysis, it shows that your calculated value of chi-square is a little below the critical value, the table value at 5% level, and you can say that the variation is not statistically significant at 5% level. And if you are not satisfied with your inference, you can go for further levels of analysis. You can go for 1% level or 0.1% level like that. So that was about tests of significance. And you see, in the case of all these tests, there is one limitation. In the case of t-test, chi-square test, etc., there is one limitation. Usually you can compare two sets of data only. You can compare one expected mean or one hypothesized mean with an experimentally obtained mean, or you can compare the means and standard deviations of two populations, or you can when you come to chi-square, you can compare one set of observed values with one set of expected values, or you can see whether different sets of observations are as per a statistical ratio, as per a probability ratio. But in that case, there should be only one observation column and one expectation column. Of course, you can have several rows of expectations and several rows of observations depending upon the ratio. If the ratio is 9:3:3:1, there will be 4 rows, both in the case of observations and expectations. If the ratio is 1:2:1, there will be 3 rows like that. But there will be one set of observations and one set of expectations. And that is one of the major limitations of this type of test. You cannot compare treatment 1, treatment 2 and treatment 3 simultaneously. Or if there are 4 treatments, 4 samples to be compared simultaneously. This pattern of analysis is not enough. This type of test of significance is not enough. T-test is not enough, chi-square test is not enough. And under such circumstances, we will move to the next level of analysis, which is known as analysis of variance. And in the case of analysis of variance, the test statistic used is F. You are carrying out F test in the case of analysis of variance. Thank you very much.